Okay, welcome to Tuesday. Alright, so we are still looking at flux, but now we're looking at how we're going to calculate EMF and thus current from this whole flux thing. Remember, flux is the product of the magnetic field times the area that it's going through. But as we saw from that early video, you only get a EMF, you only get a current if your flux changes. So we're looking at the change in flux. So check this equation here. We have our EMF, our voltage, is equal to the negative change in flux over change in time. And the minus sign will show up and be important in the calculus aspect of it. So if our flux is changing, we get a voltage. And if you remember from the video, if the flux changed one direction, you got current in one way. If you change the magnetic field in a different direction, you got current in a different way. If you don't remember this, go back and look at that video from yesterday again, the one that was on Khan Academy. Okay, so we've got the simple change in equation. And you know what? That's actually enough for some cases. If you're given an initial flux and a final flux, take the difference, divide it by the time, boom, you got average voltage. It may not be a constant change, but that's okay. Obviously, eventually we're going to get this to a calculus formula. And that would apparently be now. So we get our EMF is the negative derivative of the flux over 10. Both these equations are useful, however. If you're given a function for the change in flux, we would use the function and take the derivative. If we're not given a function and just given an initial and a final, then use that top equation, that change in flux. I've seen both questions show up, so recognize that they do mean the same thing. It's just one works with a function and the other one works with just a change value. Alright, so that's how we're going to work with this. Since more wires, more loops, will give us a greater EMF, we multiply that function by that capital N, where N is the number of loops. Think of it this way. If you have a bunch of coils of wire, they're going to be in series with each other. Since they're in series with each other, and each chunk of wire, each loop of wire will get that same EMF or that same voltage, they're in series, we add the voltages up, and you get the total voltage. Therefore, we're just multiplying by the number of coils. As you can see, that formula is labeled as Faraday's induction law. Also note, it mentions that the equation sheet doesn't have the N there. It just says change in flux over change in time, or d flux over dt. Recognize number of loops matters. It matters here for the EMF. It does not matter for the definition of flux. The definition of flux was just about magnetic field and the area of the loop. Now when we have that d flux, it could be the magnetic field changing, it could be the area changing. For example, if the magnetic field is getting stronger and weaker and stronger and weaker and stronger and weaker, that will induce an EMF. If the area is changing, that's kind of a less likely prospect. It's hard to make a coil of wire change shape, but if you are rotating it, then that would technically change that area by a function of the angle, so that would be a case where the area is changing. There are also some problems we have where a loop of wire only partially overlaps a magnetic field, and as it slides sideways, more and more field is encased, and then the area of the overlap can change. So yes, the area changing is an option, but so is magnetic field changing. So watch out for both. We'll see examples for both. So here we've got our first sample setup. Loop of wire with 10 turns. Remember, the turns don't have anything to do with flux yet. They rest in a fluctuating magnetic field. There's your changing field. Now it says the field goes from 0 to 0.8 Tesla in 7 milliseconds, so there's no function for it. It's just a change in. Loop of wire has a radius, wants to know the average voltage in the wire. So great, we're going to have to do that change in flux, but we have to look at what the flux actually is. The flux is not the 0 or the 0.8. That's just the magnetic field part of it. So first we find the flux. The flux is that BA cosine theta. Let's see, since the wire is laying in the plane of the board and the field's going into the board, that means they're perpendicular to each other, therefore theta is going to be 0. Remember, we're not looking for the angle between the coil and the magnetic field. We're looking for the angle between the normal, that projection of the coil, which would be straight into or out of the board. So that's going to be an angle of 0 or 180, so cosine of that's going to be 1. We're getting maximum flux here. B is that magnetic field, and A is the area of the loop. So we have an initial and a final. So we want to know the final magnetic field and the initial magnetic field, and those numbers are both given. The area, you've got that radius of 0.3 meters. So we do some substitution. We've got our 0.8 Tesla times our area, and that gives us our final flux, because it went from 0 to 0.8. So there's your final flux, there's your initial flux, and now we can do our change in flux over change in time. Don't forget the times n. So there's our times n, and when we calculate that out, we get our 323 volts. Okay? So this is the kind of arrangement we have to do. AP problems will sometimes ask for flux first, and then they'll do the changing flux, and they'll get the voltage. Sometimes they'll just jump to the voltage. Heck, sometimes they may just jump to current. And you recognize, oh yeah, wait, how do I get to current? Ohm's law. I need voltage. How do I get voltage? I need the changing flux. How do I get that? I need the flux. So remember, some AP problems will go quite a ways down the rabbit hole and give you the last answer, or last question. You've got to go through all the steps to get to it. Sometimes they'll walk you through it. It really depends on the year. So think about that for a second. Do those calculations again, write them down, and make sure you get those same numbers. Make sure you're kind of locking in on that procedure. All right, another sample problem. Here we have a loop of wire. The magnetic field's changed a little bit. It's going from a negative magnetic field, and it reverses. So it goes from 0.8 Tesla in one direction to 0.8 Tesla in the other direction. Also, the loop of wire was rotated 20 degrees, so that projection is no longer parallel to the magnetic field. It's now at an angle of 20 degrees. Let's see, we know the magnitude of the voltage in the wire. So, again, we first find that flux. Find the initial flux, find the final flux. Now you might say, oh, well, it's 0.8 Tesla, 0.8 Tesla. It's the same flux in both cases. Well, if that was the case, you'd have zero change in flux. So the flux actually changes direction. Your flux is one way initially, and it's the other way afterwards. So the magnitude's the same, but flux does have a direction relative to that loop. So, yeah, I don't want to get into clockwise, counterclockwise. It's not quite that way, because it's a vector through a hoop. So, suffice it to say, our flux is one direction before and a different direction the other. So the delta flux is double, going from 0 to 0.8. So if you look at the final minus initial, we do keep track of that minus sign here, and we get a larger change in flux. Now, of course, we are going to, at that point, go ahead and do the change in flux, which is our 0.425 Webers. Do that over the change in time, and we get a different voltage. Now, the voltage is larger because we had a bigger change in magnetic field, but it's not double what it was because we did change the angle a little bit. So the actual amount of flux is smaller because of the smaller view of that loop. Okay, great. So that's the idea. Watch out for angles. Watch out for changing flux and how is it changing, reversing, going from something to zero, zero to something. The little details. But all the algebras lay out the same. So make sure you're following that. Okay, now let's see if I can animate some of this stuff. So we talk about Lenz's law. You know what? I'm going to start a fresh clip of video. Pause a moment for me. Okay, so we have a mathematical formula that allow us to calculate the magnitude of the EMF based on a changing magnetic field or a changing area. Fine. Formula for that. Remember, to get the current, you're just going to do Ohm's law at that point. Calculate the EMF using those calculations, use Ohm's law, V equals IR, and that'll give you your current. Now, the next question that they're often going to ask is, what direction? What direction is the current that's induced? So, look at Lenz's law for this one, and let's focus on the idea that if the magnet goes into the solenoid, it's going to create a current. But also remember that current in the wire is going to create a magnetic field, and the direction of the current in the wire determines the direction of the magnetic field in the wire or inside that loop. So if you look at the picture as drawn, It does not show you which way the current is in the wire, but it does show you a magnetic field generated by it. So I'm just doing a little right-hand rule myself right here. I'm holding my hand up, grabbing the wire. Magnetic field is coming out. So it looks like the current on the right is up, and the current on the left is down. Yep, current on the left is down, and then put a magnetic field into the solenoid. Okay, that's the idea. If we had current in the wire creating the magnetic field. So there's definitely a relationship on those directions. But now, let's take this magnet. We take the magnet and we go to push it into the solenoid. As we push it in, it's going to generate that current. Now there's two possibilities. The current could be in such a direction that the magnetic field pulls this magnet in which case it accelerates and gives us more current, which gives us more magnetic field, which gives us free energy, and we know that can't be right. So therefore, by process of elimination, when we push that north end of the magnet in, the magnetic field must be to the right, so that the north pole of the interior magnetic field is to the right. Pause, jump that back, play it again, listen again. So the magnetic field inside the solenoid has a north end to the right. In order for the magnetic field inside to be to the right, then you must have a current that goes down on the left and up on the right. So you have to imagine the current creating the magnetic field, because they go together. So if we're creating a magnetic field, let me rephrase that, if we're shoving the magnet in there and it's generating a current, it would generate a current which generates a magnetic field that fights what we're doing. There has to be some resistance because we're doing work. When we go to pull that magnet out, again, it's going to generate a current in such a way that the magnetic field inside will resist what we're doing, which means we have a south pole to the right inside the coil and the north pole to the left, which means the magnetic field would go opposite what the diagram shows, and that means the current would reverse as well. So there's a definite relation. I'm going to go take a look over at Khan Academy, see if there's any good animations for this, or I'll do some other searching elsewhere, see if I'm pulling up to follow this. But that's the concept. Direction of motion of this internal magnet is going to generate a current which will give a magnetic field inside the coil that fights the motion we're doing.
So right over here I've depicted a square loop of a conductor. Let's say it's a wire and it's stationary and it's sitting in a magnetic field. And I've drawn a few vectors that represent the magnetic field. And you can see at least on the surface that is defined or that's contoured by the wire that the magnetic field looks constant. So if we just had this scenario, nothing too special going on, but it becomes interesting if I were to actually change the flux going through the surface. So both of these pictures right over here, they actually show the same scenario where we have increased the flux. We have increased the flux at these points on the surface defined by the wire. At every point, the magnetic field has now gotten stronger. So we have increased the flux. So let me write that. The flux, we use the Greek letter phi to usually denote flux. The flux of the magnetic field, has gone up. And we know from Faraday's law that when you have a change in your flux, that's going to induce a current in the loop. And so an interesting question is, what direction is that current actually going to go in? We have two options. The current could go, let me find a nice color for the current. The current could go in the clockwise direction, or it could go in the counterclockwise direction. So which of these two do you think the current will actually go in? Well, let's think a little bit about it. We know that a current flowing through a wire actually on its own will induce a magnetic field above and beyond the magnetic field that's already there. So let's think about the type of magnetic field that this orange current would actually induce. So if it's going in the counterclockwise direction, remember we use the right hand rule. I can take my right hand, point my thumb in the direction of the current. So let me see if I can do that. So my thumb in the direction of the current, and then my hands are going to loop, or I should say my fingers are going to loop in the direction in the direction of the magnetic field. So when I do that with my right hand, so my right hand looks something like that, thumb in the direction of the current right over here, we see that it shows a magnetic field being induced that would wrap around like that. Or if we were to show it, if we were to sample it points right on the surface, the magnetic field that would be induced would look something like this. And I'm just doing it at some sample points. So notice, it would be additive. It would be additive. Whoops. It would be additive to the existing magnetic field. In fact, it would increase the flux even more. In fact, at these points, these vectors would increase even more. These vectors, let me see if I can draw that. These vectors would increase even more. Well, what would that do? If the flux increases even more, then the current is going to increase. The current is going to increase even more, which is going to make the flux increase even more, which makes the current increase even more. And you would have this never-ending cycle where the current keeps increasing and the flux keeps increasing, and you would have this energy that's appearing out of nowhere, which would violate the law of conservation of energy. And so that's a pretty good argument for why you would not. That's a pretty good argument for why we would not expect the counterclockwise scenario. We would not want the current that's induced to induce a magnetic field that goes in the same direction as our increase in flux. So just by deductive reasoning, we know that this is going to be the scenario. And let's think about what happens here. We can do the right hand rule again. We take our right hand, point our thumb in the direction of the current, point our thumb in the direction of the current, and we see if we do that with our right hand, well, now this would induce a magnetic field that would decrease the flux. So it would produce a magnetic field. The current right over here would produce a magnetic field that's going downward. The current in that direction would also, when you take your right hand and you were to put it along here, once again, if you are going in the counterclockwise, if you're going in the clockwise direction over here, that too, when you do your right hand rule right over here, your fingers would coil around that way. And so once again, when you look at the surface, it would induce a magnetic field that is going in that direction. And so it would have the induced magnetic field from the induced current will go against the change in flux. And this makes sense because we won't go into this never-ending positive feedback loop where the current keeps getting stronger and stronger and the flux keeps increasing and increasing and increasing. And this idea that the orientation of the current that is induced will produce a magnetic field that counteracts the change in flux. This is Lenz's law. Lenz's law. And once again, if that wasn't true, then you would have a violation of the conservation of energy. So in general, whenever if someone says, okay, well, this is the change in flux is happening in a certain direction, well, to think about which way the current would flow, you just have to say, well, what type of a magnetic field would each direction of the current produce? And that magnetic field should go in a direction that goes against your change in flux. So if the flux is increasing, the magnetic field that's induced by the induced current should make the flux decrease. If the flux was decreasing, then the induced magnetic field by the induced current should make the flux decrease less, or should make the flux should be additive to the flux.
Okay, so that video, credit Khan Academy, that video shows the idea of if you have a changing magnetic field, you're going to get an induced current. So this is a similar diagram to what the video showed. You've got a magnetic field coming out of the board. You've got the loop in the plane of the board. And at the moment, the question is, which direction is the current? I would wait for the class to respond. We would discuss it. And the answer would be, there is no current. You have a constant magnetic field. Constant magnetic field does not yield an EMF. If we had a increasing magnetic field, now we would. If that magnetic field gets stronger and stronger and stronger, then that means you would get a current induced, an EMF induced. Now, looking at it, if the field's getting stronger, we would want to use right-hand rule, and the other guy's diagrams were much better than mine, so that's why I showed his video. We would get a current. We could not get a current over here upward, so the current over here was upward. Then we'd get a magnetic field coming out of the board in this region, using that right-hand rule, and that would make the field stronger. And we have to fight that change. So that means the current here would have to be down. So recognize from that other video that any change in magnetic field is going to induce a current that's going to resist the change. If this field were getting stronger, or sorry, let me rephrase, if the field were getting weaker, then a current would be induced that would bolster it and try and keep it strong. So it would create a current upward over in this region, so that the magnetic field here created from that current would be out of the board, and it would try and keep it that same strength. Basically, it's trying to resist change. Don't think of it as momentum or inertia, but it is resisting any change in that region or in that magnetic field. And that's how you determine the direction. Another cool demo we just can't see right here. You know what? I bet I can find this one online, and I got a video on my machine, so let me track those down.